Hello, my name is Jacqueline Dean. This is my 2212 Lab 5 named Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction computationally, and compare your data computational predictions with your observed data. Some important initial physics concepts include Faraday's law, which is that EMF is equal to negative delta phi over delta T. We have the Biot-Savart law, which is important to find B, Ohm's law, which is I equals V over R, and magnetic flux. Here we can also see an example bar magnet for this experiment in which we see that the force of the magnetic field is equal to the force of gravity. A few assumptions for this lab are going to be that air resistance is negligible, the bar magnet is equal to the magnetic dipole, and the only forces acting on this magnet in the system are gravitational force and the magnetic force. Now we have the data and model. The system is the aluminum foil and the magnet, the surroundings is everything else. Some initial conditions are that the magnet has no velocity, it is stationary above the magnet and has not yet been dropped, and there is no magnetic force. The tube length measured is 0.35 meters, the width of the aluminum foil is 0.0008 meters, the mass of the magnet is 0.026 kilograms, and the magnetic dipole is 5.841. For the experimental data, we can see that trial 1 took 1.13 seconds, trial 2 took 1 second and 7 milliseconds, 1.09, 1.11, and 1.1 seconds over 5 trials. The average is 1.1 seconds overall of the trials. This is very blurry because this video has probably been exported and imported 15 million times, but here's my experimental code for the GlowScript model that will be on the following pages. Here we can see the beginning portions of the code, if you can even see it because it is very blurry, I do apologize. And here's the remaining portion of the code used in the GlowScript model. Here we can see the overall velocity versus time graph that the GlowScript model has produced based off of the data that we have put into our GlowScript code. Here we can see a kind of decrease in time as we go along. Causes for discrepancy in this lab include human error, bad math, rounding errors, wrong code, etc. Now for our what-if questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The answer is that the magnet would never fall through the tube. This is due to the braking force increasing and being equal to that of the gravitational force. And our final question for the entire semester, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnet would fall faster through the tube because there's a reduction in the flow of current. The braking force would decrease in strength. This is because gravity is more influential under these conditions than that of the force of the magnet. This is the exact opposite force, or the exact opposite results that we saw in the first what-if question. Thank you so much for watching.